Hi everyone. In this video I'd like to walk through a little bit of work on looking at tables involving exponential functions primarily, but I'm going to throw linear in the mix just to make sure that we're still thinking carefully about how linear relationships work. So this one is entirely filled in for you. All I want you to do is look for the patterns. So this top row gives the formula. This is our y equals whatever's in the top row. And the first column gives us our x values, and then we see the outputs, the y values of this general function at the top. So the first one is definitely linear. A y equals 3x plus 7 is a linear function. If you look at the table, you should see a nice linear pattern. A linear pattern is one where you add and subtract the same number, add or subtract the same number over and over and over again. So here, if I increase my x by 1, my y is increasing by 3. If I increase my x again, my y also increases by 3 there. All the way down the table, every time x increases by 1, y increases by 3. It is not a coincidence that this 3 is also the slope of the equation. That's what a slope of 3 means. It means if your x increases by 1, your y increases by 3, or you could read it as your x always increases by or your y always increases by 3 times as much as your x. Make sure I say that in the right order. The other thing to notice is we had this value of 7, this constant added on, and that shows up right here with the input 0. That is also not a coincidence. So this row right here is the y-intercept row. Those are the y-coordinates of the y-intercepts of each function. So linear function, this is increasing linear function. You see repeated addition, and you also see the y coordinate of the y-intercept sitting there at x equals 0. Second one is definitely exponential. We have a 2 times 3 to the x. If you look at the pattern, it might be a little tricky at first, but I hope that at least towards the end you catch that what's happening is I'm multiplying by 3. And it does hold here. 3 times 2/9 is 2/3. 2/3 times 3 is 2. So this base is telling me what I should multiply by over and over and over again. Once again, it is not a coincidence that the 2 sitting here matches the 2 at the top. The number out in front in your exponential function should represent the y-coordinate of your y-intercept. Unless you start doing some crazy vertical shifts, that should be absolutely fine. Okay, negative 2x plus 1, that's definitely linear, and it now has a negative slope instead of the first one that had a positive slope. So if we look at the table, 5 to 3 is down 2, down 2. It looks like that's going to hold all the way through. Okay, so again, we're seeing the slope show up. That's what's dictating this pattern where we get this constant decrease for every unit increase in x. And we see the 1 showing up in the y-intercepts row again. Okay, very last one, negative 3 times 1/2 to the x. So that was a decreasing linear. This one, multiplying by 1/2, should make things smaller. So here we should be seeing exponential decay. And this is what it tells me should happen. Excuse me. Multiply by 1/2, but we can double check it. If we multiply the 12 by the 6, that's a 1/2. If we multiply the 6 by the, they're negative. Negative 12 by 1/2, we get the 6. If we multiply the negative 6 by 1/2, we get the negative 3. If we multiply the negative 3 by 1/2, we get negative 3/2. And if we multiply the negative 3/2 by 1/2, we get negative 3/4. Okay, so this is what a linear versus an exponential pattern looks like. Linear is repeated multiplication. Exponential is repeated addition or subtraction. So this next part, I want to see if we can look at each of these tables and spot which is a linear pattern, which is an exponential pattern, and then find the appropriate equation for the linear or exponential. And I'm specifically looking for linear equations to be in the form y equals mx plus b, and exponential equations be in the form y equals ab to the x. Okay, so x, y right here. So if we're looking for a pattern, I see that this is 4 apart and this is also 4 apart, and this is also 4 apart. So it looks like I'm adding 4. So just remember to think about whether it's repeated addition, which would imply a linear relationship, or repeated multiplication, which would imply an exponential relationship. As soon as we've got this, when x increases by 1, y increases by 4, we've got our slopes. That's a rise-run pair. 4 over 1 is equal to our slope. If we're going to find an equation, we also need to know the b, so the y-intercept, and we're lucky in this one it was given. So b is equal to -1, which means my equation is y equals 4x minus 1. So I'm not changing any of the rules about how you find equations for linear functions. I've just organized the information in a table for you. So try not to let that throw you off. It really is the same thing. Look for a slope. If you like, if it's not easy to spot, you can go ahead and take change in y over change in x. So subtract a y2 minus y1 and an x2 minus x1. Number 2, I think, is a little more hidden. I don't really love seeing the improper fractions. The mixed numbers, I would much rather see an improper fraction. So I'm going to go ahead and get a common denominator. So I'm going to say 1 is 3 over 3. If we then add 1 over 3, we're getting 4/3. 2 is 6 over 3, which means when we add 2/3, we get 8 over 3. 5 is 15 over 3, plus 1 is 16 over 3. And 10 is 30 over 3, so we end up with 32 over 3. And now I think it's much more obvious, although you probably could have spotted it here if you looked at it for a minute. I think this makes it a lot more obvious, though, that what's happening is we're doubling our y over and over and over again. So 2 times our y value every time our x value increases. We are now going for this y equals ab to the x form. The a should be the y-coordinate of your y-intercept, and in this one, the y-intercept didn't show up on my table, so I'm going to have to think carefully about that. The b value did. I'm multiplying by 2 over and over and over again. So every time x increases by 1, y doubles, which means I need to be multiplying it by 2 to the x. So there's more than one way to find your y-intercept. One would be you could just put an a in here and then plug in any one of these 4 points for x and y and solve for that a value. Since we have a table, I kind of like continuing to work with my table. So I would just say if moving yourself down the table run row decreases your or doubles your output, then moving one up should cut your output in half. I keep wanting to switch input output. So before 4/3, we should have had 2/3, and before 2/3, we should have had 1/3. So this would be the 1 and the 0, which means my y-intercept is at 1/3. So I have to compress horizontally to make that true. Okay, next one. I'm seeing 3/2 to 5/2, which is a space of 1. And then I'm seeing 5/2 to 3, which is a space of 1/2. And then I'm seeing 3 to 5, which is a space of 2. So this is looking a little messy right now, but I think it's doable. The thing that's actually making it messy is we're skipping some values. So really there should be a 0 here in the mix, and then a 3, 4, 5 if we want to see the perfect pattern continue. -1. Oh, putting it in the wrong spot too. 0 should go in here. That's better. Okay, -1, 0, 1, 2. So if we want to figure out what goes with 0, we need to figure out what we're multiplying by, or adding, subtracting. In this case, here, let me just redraw it so I can space it all out. If we had a -1, 0, 1, 2, 3, and that went with a 3/2, a 5/2, a 3. So if we can figure out 5/2, there we go, the spacing, we can do it right here. These are half a unit apart, so multiplication isn't looking hugely promising to me because I have to go from 3/2 to 5/2 to 3 to 5. That doesn't seem like a nice easy multiply. So I'm going to say maybe I'm adding 0.5 each time, which would mean at 0 I would get 1.5 would give me 2, and then at 1 I'd get 2.5, which matches up. At 2 I'd get 3, which matches up. And you could continue this, and you should see that if you plug in 6, you get 5. If you plug in, I think I already said it, 2, you get 3. So the pattern that we have in this table is that, here, let's see, what did we get here? 2. From here to the 2 is that what we're doing is adding 1/2. Every time our y value, our x value increases, our y value should increase by 1/2. So my equation, this does appear to be linear, has a slope of 1/2. Can you see that still? Yes, good. See the tops. And it has a y-intercept at 2. Okay, very last one. My x's, I am skipping some spaces, so we skipped a -1, we skipped a 1, but we have -2, 0, 2, 3. I see that -2 drops to from 45, so when x equals -2 we get 45. Y equals 45 drops down to 5 by the time we get to 0, and then down to 5/9 by the time we get to 2, and down to 5/27 by the time we get to 3. So for one thing, yeah, okay, from here to here, it looks like I divided by 9, and from here to here looks the same. It doesn't hold for 27, but notice 27 doesn't have the same spacings as some of these up above. So one of your options, I'll give you a couple, would be to say, okay, I'm going to say this thing starts at 5, and then it gets multiplied by 1/9 every 2 x values. So from -2 to 0 and from 0 to 2. If you want to show that it happens every 2 x values, we are trying to slow it down, so we would do an x divided by 2. So that's one perfectly valid way to do this. Another is to pick out, so for example, we could use the same 2 points if you want to. I think there's an easier pair, but it might not be bad to see. We want to know if we start at 45 and we multiply by some base, and we get 5. Oh, let me do this carefully. We multiply by some base 2 times. So to get from -2 to -1, we multiply by the base once, and to get from -1 to 0, we multiply by it again, which means 45b squared equals 5, or b squared equals 1/9, which tells me that b is plus or minus root 1/3. I don't see sign swaps happening, so I'm going to go ahead and go with the positive 1/3, which means if I filled this in, for -1, I would have 45 times 1/3, which is 15. For 0, I would have 5 times 1/3, which is 5. Great. For 1, I would have 5/3, still looking good. 5/9, 5/27, that looks perfect. So we also could say that this is a 5 times 1/3 to the plain old x. That this thing starts out at 5, and the y values get divided by 3 every time x increases. All right, thanks for watching.